Okay, this is a walkthrough of the machine learning explorations you will be doing for class this week. This would be week 11, and you can find the video here once it's done, but you're already watching it, the tutorial, and then there will also be the code base. Will be here as well. Excuse me. Okay, so this code or the tutorial is based on the W3 Schools machine learning, the 13-part machine learning tutorial that they have. So what I recommend you do is don't look over here at this weird t-shirt, but go through and follow each of these steps, and every time they let you try something out, so nothing to try out there, but as there are things you can try out, run those examples and give them a try, click run, and then you can change things. So, oh, now it's going to take a while. There it is. So if you changed this, now the mean of this is, well, it's going to be different. Let's really change it. So as 89% was the mean, we added an outlier and it's doubled. Okay. So anyways, each time you run the examples, tinker with it a little bit so you know that you know what's going on. Okay, so as you go through it, you're going to build up some code and you're going to try the things, and they're going to have a code base that you are going to use. And their code base is about, it starts here with the percentile. No, I was wrong. Data distribution. Their code base is about cars sometimes. Sometimes they just do random numbers. So here, this is a way to get random numbers. So they're getting what, 100,000 random numbers between 0 and 5. And then they're plotting it. And I think you should definitely use this as you go through. And eventually, scatter plots, eventually they get to a point where they're using cars as their data set. But what do you care about cars, right? I mean, is it interesting to know the CO2 output on a car based on its volume and weight? Yes, possibly it is. Here that calculation is. But you might care about other data. So go through all of this, including the scale and training and testing your model. And then finally, what a decision tree is and how it works. Okay. But when you're done with that, then pick your own data, pick data you care about. That's what I'm going to show you next. Okay. So I'm picking, and again, this is from class, so you probably have it in your project. I've got something called seasonstats.csv. I can open that up and it might look like this. It's text formatted, comma delimited. But if I open it under the data tab within PyCharm, I get this nice table. And so it's showing all the columns and then all the values. And it's about 14,000 rows long. And it's got about, I think, 51, 53 columns going across. You'll notice that a bunch of the columns don't have anything in them. That's because in 1950, they didn't keep track of things like PER. They didn't even have a 3-point line. So how could you keep track of 3-point attempts? I think that's what that is. Anyways, so what you would do is you'd pick data you care about and you know intuitively. So then when you do things, you can either get insights or you have a sense as to whether it's working or not. I don't care about cars that much. So I'm going to use this NBA data set. You could use other data sets. I was hopeful we could use data sets coming from UNL Canvas, but it's not quite ready yet. So I'm going to use this one and I'm going to show you how I'll build it up. Okay, so first we're going to bring in all the import options. So all the packages, external packages, you will probably have to add some of these. For instance, the pi.plus you'll probably have to add, and then you'll probably have to add graph viz, and you might have to install the executable. And if you do, here's the URL for that to download it and install it. Okay, so once you have those, then we need to do a few things. So we're going to set a standard scalar. And then we're going to set it up so that you'll notice up here, Pandas is PD. So this line 17, Pandas set option display max columns equals none. So this means this is like a maximum here. So display all the columns because I want to see everything that we've got. Okay. Next one is we have to get the data and read it in. Now, you'll notice I don't have a path here, and that's because seasonstats.csv sits within my project. If yours sits here too, you can just call it. Otherwise, add the path to this so that you can find it. And we've done that in the past, so look at that code and grab that code. You don't have to learn it again. You just have to locate your code and do the same thing you did last time. Okay. Trying to delete this as I go. Okay, so now I want to do a few things. So I'm going to bring in 3 lines of code at the same time. Okay, so I want to print the first like 8 rows just to see how it looks. And then I want to get the names of columns and types of those columns. So let me run this. Come on. Taking a little while. There we go. Okay, so you'll see here, since we set the max columns to none, then it's showing us all the columns. So the first thing it does is it brings in the first 8, but it's bringing them in up to a certain width. And then this backslash means look at the next chunk. So these match up with the ones above. Okay, once we get through that, here we have the column names, and then we have the data types. So for each column, the year is a float, the player is an object, et cetera, et cetera, et cetera, et cetera. This is useful when you're trying to compare values sometimes. It won't let you, and you look, oh, the data type is off. So you can change the data type or do whatever you need to do to work around that. Okay, so that just gives us a sense of our data. Now you notice that there's missing data, and we've got to deal with that. So before we deal with that, let's also get the shape of the data. So the existing shape of the data before we trim it or change it is going to be this printout, and it's going to be how many rows and how many columns. So if we run that again, it should be faster this time. Yep, and so here's the data shape: 24,690 rows and 53 columns. But we want to drop some columns. We want to drop columns that don't have any values in them. There are a few of those. So if any column is missing every single row all the way down, we want to remove it, because otherwise when we remove rows with missing values, it'll remove all the rows. And then we're going to get this how many, what's the shape after we do this. So let's run this again. And you'll notice that ingested data shape was 24,690,53, and now it's 24,690,51. So it got rid of 2 columns that didn't have any data in them. Now, guess what we're going to do? Yep. We are going to drop rows that have missing data. So you remember up here, we've got people from the 1950s who don't have certain things like PER or steals or blocks. So we're just going to eliminate those. We're dropping rows, any row where there's any missing data. And then we're going to reprint that shape. Okay, so we went from 24,690 rows down to 14,558. Still plenty of rows. Goodbye 1950s basketball. Okay, the next thing we're going to do is we're going to reduce further, but by particular columns. So in order to do that, we are going to add a little function here at the end. And so this is the get data function, but what it really does is it creates a new data frame with only certain values that are at a certain level. So this is saying, okay, pass the data frame, give us a value, a numerical value, and give us a column name. So then the new data frame equals the old data frame that was passed, and in the location of this column, keep only rows where the value is, or the row value is higher than this score value, and then return that new data frame. So here we've got NBA test is the variable that's going to hold our new data frame, and we've got it set at get data NBA frame 50, and this is free throw attempts. So we're only keeping rows for players who had 50 or more free throw attempts. If that's too many, you could always reduce it down to 20 and then go from there. And then NBA test. So you notice we've got NBA frame here as the old data frame, and here we've got NBA test as a new one. And so first we're calling anyone who shot less than 20 free throws, because that's not very many free throws. They didn't play very much, probably. They weren't really into it. So we're just going to eliminate them. Then on this, we're going to run this same get data again, but this time we're going to update NBA test on NBA test, but we're going to look in the year column for every row. And if the year is greater than 2016, we're going to keep it. And this data only goes through 2017. So we're basically getting rid of everything that isn't 2017 season data. Okay, so let's run it. And then we should probably get the shape again, right? So let's add that down here. After dropping rows with fewer than 20 free throw attempts and from seasons before 2017. Okay, so now let's run. It's a little slow. There we go. Oh, you see what we did wrong here? Look, this value is still pretty high. What is the problem with line 40? You see this? I didn't change it from NBA frame to NBA test. So now if I run it, there we go. Look at that. Now we've dropped down from 14,000, from 24,000 records to 14,000 down to 412. Okay. And I'm going to pause it here for a second. Okay, meeting over. Where were we? Yes, so we drop those rows and we end up with 412 rows or players across the 51 columns. Okay, so what do we do next? Well, we're going to create a column that doesn't exist, because what we want to do is we want to predict something based on all of this. So we're going to add a column to the data frame. On line 42, you can see it, and it's called All Star. And we're going to set the default value. So this column does not exist. We're going to set the default value to 0. And in computer language, as you know, 0 usually means false, untrue, no. So 0 means not an all-star. And then for 2017, I went to Wikipedia and got a list of the all-stars for both the East and Western Conference, reserves and starters, and I'm pasting them in here. So I turn it into a list, and so each all-star is in this list, and the list is called all-stars, as you see, all lowercase. You'll notice it's all lowercase, and this all-star uppercase singular is the column name. So they're pretty similar, but don't confuse them. Okay, then what we're going to do is we're going to use this list to look at every row and change the value from 0, not an all-star, to 1, an all-star, if the person is in this list. So here, it takes this NBA test and it looks at the location of player, and it compares where the player is in this list. So remember, player up here is their first and last name. So that's where player comes in. And so in the player column, if the player is one of the people in this list, then change the all-star column value to 1. In other words, they are an all-star. Okay. So then let's print out, and let's print out the first 18. Let's see if we get an all-star in this group. So let's run it. And so you'll notice at the end here, all-star is a column. Let's do dot tail, do the first 20. Is that how you do it? I just want to look at the last 20. Oh, okay, so here's all these all-stars are listed as no. And if we go up to the names of the people, Deron Williams, he was an all-star, but not in 2017. Lou Williams, Marvin Williams, no, none of these folks are all-stars. I was trying to get to John Wall. Let's go to 29. Run it again, because John Wall was an all-star in 2017. Oh, there's one. Okay. So now let's go up. And, oh, Russell Westbrook. So we didn't make it to John Wall, but Russell Westbrook, the third one here, he was an all-star in 2017 for sure. And he's the third one here. Okay. So I'm going to take this out. And now let's check the shape. Well, it should just be one more, right? One more than it was before. So let's skip checking the shape. And now let's There we go. Come on. Okay, so we're going to test if effective field goal percentage and free throw percentage are correlated with 3-point percentage. And you notice we've named them. We get a scaled. So remember when we set scale up above? So here we've got scale.fit transform. And we may not need to use it given that all of these are on the same scale. And then let's run a linear regression model. And let's do these three. Okay, so we've got a linear regression model here. And then we've got scaled transform. And then here we're predicting the, well, we're predicting the 3-point percentage, not free throw percentage. I changed it, but I didn't change the variable name. Terrible, right? Okay, predicted 3-point percentage, and then we better change this one. 3-point percentage. Okay, so the predicted 3-point percentage is based off of these two. So if the person shot an effective field goal percentage of 51%, and I think this was back from total free throws. So let's change it to 0. Let's say they're a 91% free throw shooter. Okay. Let's see what happens now. Okay, so this is predicting that if their effective field goal percentage is 51% and their free throw percentage is 91%, then their predicted 3-point field goal percentage is 39.3%. So if we change this, let's make them a terrible free throw shooter. Let's make them a 31% free throw shooter. Now let's see what we get in terms of predicted 3-point percentage. Ooh, now it thinks they're going to make only 7% of their 3-pointers. Okay, I hope that makes sense to you. Let's add some more. Okay, let's do a scatter plot of the free throw percentage across 3-point percentage, and then the show. So this is going to be math plot library. So let's run this. We should get a graphic showing up over here. There it is. And if we zoom in, okay, we've got one person who was shot 20 for 20 on free throws, but otherwise, we've got a bunch of people who didn't shoot well at all. Otherwise, we've got effective, this is probably effective field goal percentage. So this is probably someone who only took 2 or 3 shots. And these are a bunch of people who only took a few shots and missed. And this is only took a few shots and made them all. Anyways, everyone else, so we could call this, just like we did for free throw attempts, we could call this and say that, hey, if they didn't take enough field goal attempts, we don't count them either. And then that would clean these up. And then in between here, we've got, here's free throw percentage on the bottom. And then this is effective field goal percentage. So as the, like, what can we say about it? Can we say very much? Maybe we can say that, you know, as you get better at free throws, does it go slightly up? Anyways, let's continue. Actually, let's go up, and what if we tinkered with this one, with this free throw attempts? What if we made it field goal attempts? Is that a column? Field goal attempts. FGA, field goal attempts, there it is. Okay. So let's add that here. And let's make it 20 shots. Oops, FGA. Okay, so now when we rerun this, this graph should change. We should get rid of this top and these bottom ones. Let's see if that happens. Cross your fingers. Well, some of them went away. Some of them still remain. If we change this to 50 field goal attempts. Okay. Well, let's keep going. I don't think that was super illuminating. I've got more questions after that than answers, which means I still have to dig around to figure it out. But let's keep going. Okay, so in order to train a data set, you want to have a training set and then a testing set. In your training set, you might have as 80% of your entire data set. So in this case, what I'm doing is we're saying, okay, let's get how many of the existing rows is 80%. And these are going to be the same because this is going off of free throw percentage, like the length of X. So the length of this, how many rows are in this column, it's going to be the same as the number of rows in this column. But since we've got both, I just did both. All right. And then we're going to want to train on the training set of that 80%. So here, this is taking from 0 from the first record until it gets to the number that equals 80% of the total. And so it's training on that. And then you'll notice here, it's a nice little trick of lists in Python, is that the test set is then the 20% that's left. So all you do is you just put that number, which represents the 80%, you just put it on the left-hand side. And then on the right-hand side, you don't put anything. And that means that start at this, take everything that starts at this row number and goes till the end. Okay, then let's show this. And run it. So now we're going to get 2 There we go. So this is the training data. It should look a lot like the last one. It just has a few fewer dots, right? Because, well, it's just the ones, it's 80% of the total. Now let's do the same with the test data. So this is just going to be 20%. We'll get another graph. Oh, well, that looks a little different, but part of the reason it looks a little different is probably because the scale is different, right? This is going from 50. So once you get rid of that, if this perfect one up here doesn't exist, then you can zoom in more. So I'm going to say that this is probably the same. I mean, it's similar to this one. It's just that this is skewing because of this one. You should figure out what that is and eliminate it. Okay, now let's build a model. Okay. So this model is going to be based on the polyfit NumPy model. We're going to use our training data, and we're going to draw a line of fit through it. I think that's what we call it. And let's see what happens. And then we're going to show it. Okay, so you can see here it's just splitting the difference between these two and then splitting the difference between these and then right through the middle. And now, let's go back. I want to get the name right on this, so I'm not just making something up. Let's go here to the decision tree. And if we go to the training and testing one, this looks a lot like ours, although ours is slightly different. Train the data. Yep. Yeah. Fit the data set. There's where it fit. That's what we did. And then we've got this R squared, which is regression. And how well does it fit the regression? And 0 means no relationship. 1 means complete relationship. Okay, so then let's run ours. So let's grab it, paste it in. And so let's see what we get in terms of this relationship. We're going to quantify it. Down here, it's 0.17. So not a huge relationship, right? It's pretty close to 0. It's way closer to 0 than it is to 1. Tells you something, but maybe not everything. And then if we go to the test, you can grab that. Put that in there. Please stand by. There we go. Okay, so the test data, it fits slightly better, but pretty much the same. Okay. Oh, and then, so then we can grab this. So you'll notice up here we've got XPTS, test X is free throw percentage. So free throw percentage is estimating, like we did before, is estimating 3-point percentage. So down here, if we put in 90% free throw percentage, what do we get? What's the estimate for 3-point percentage? Again, a good time to take a break, take a drink. And it's guessing that your 3-point percentage would be 0.9. So I'm just gonna, so all the variables are hanging out down here in the terminal. So I can come down here, instead of running this again, which might take a long time, what if we set this to 70% instead of 90? Let's see what happens to this number. Would this go from 36.5% down to 29%, 29.2%? So 3-point field goal percentage has probably gone up since 2017. But this is a predictor. That's why one of the things they'll check for draft picks coming into the NBA is they'll look at their free throw percentage. And if they're shooting, if they're an 80% free throw shooter or a 90% free throw shooter, and they haven't made a lot of threes, they'll feel like, well, this person can learn to shoot 3-pointers because their free throw percentage is so good. If the free throw percentage is terrible, they're like at 40%, ooh, look out. Let's even do 50% field goal free throw percentage. And it says, yeah, they'll probably be an 18, 19% 3-point shooter. Okay, again, you might not care about basketball and these things, but I'm using data that I have an intuition about, which helps me understand the concepts that are happening and what they mean and what they do. Okay, now let's make a decision tree, because that's the last part of this machine learning is a decision tree. And so let's make one based on this basketball data. I mean, you could use the comedy data, and you hopefully did. But let's try it out. So the first thing we need to do is we need to turn some values into numbers. So you'll notice here, they've got the nationalities, and they've got US, UK, and then neither, which is problematic. But you get the idea that here they're changing UK to 0, US to 1, and N to 2. We're going to do the same thing in our code for the position that they play. You see the position here? They've got guard forward, small forward, forward guard, et cetera, et cetera, et cetera. Okay, so we want that to map to numbers. And the numbers, like the quantity, like a higher number doesn't mean anything. It's sort of like a variable that says, oh, if you're a 5, that means it's a center. So this is a dictionary, and it's got all the permutations from point guard to guard forward, small guard, et cetera, et cetera, et cetera. So this is just holding the position mappings. And then let's update our data frame. So NBA test position equals NBA test position. And then it says map this position mapping. So it'll go through, and every place it sees a PG, it'll replace it with a 1. Every place it sees a G or a GF or a SGPG, it'll replace it with a 2. Should eventually be an SG by itself. Yeah, there it is, SG. And then it goes through 3, 4 for power forwards, and centers are 5s. Okay, so that'll update that column, so we will no longer have PG in there. It'll be a 1 or whatever. Okay, so then we might want to confirm that that worked. So we might just grab the last two instances. Good chance to get hydrated. And here we go. We've got All-Star 0, 0. Well, we already had that, right? These two people did not make the All-Star team. We're looking for position. We've got a 3 and a 5. So Zubac is a 5, which means he's a center. And Paul Zipser, never heard of him. He is a forward, playing for the Chicago Bulls. Played 44 games. Okay. Anywho, it worked. There was much rejoicing. Okay, now we need to know what features are we going to use to build our decision tree. And so what we want to do is we want to look here and we want to say which of these features is most likely to lead to an all-star selection or be able to help you figure out all-star selection. We should probably go to the bottom because there we have, here we've got the 2017, and we've got the full column and what the values are, but then we can't see the columns. So we're back up here at the top and we've got a bunch of different ones. So we've got something called WS, win shares. How many wins is this player responsible for? Look, you've got some people who have negative win shares. So the people call them a losing player. You put them in and they make it harder for your team to win. Some people, you put them in and they make it much easier for your team to win. Here we go, 5.3, 9.2, sign them up. Okay, and then we've got field goal percentage. There, at some point, there's a PER, which is a player efficiency rating. Anyways, we're going to pick columns, and the ones I picked were age, position, PER, and win share. So I thought, well, you know, maybe the position they play plays some role. Maybe their age plays some role. How efficient they are and how many win shares they're responsible for has something to do with it. So then we've got an X and a Y. Our X, we already used X, so I'm using double X. We've got features. So this is saying in this data frame, grab all, like look at these columns, these 4 columns, and then for the Y, for the test, if they're an all-star, grab the all-star column. Okay, and let's make the tree. Okay, so the decision tree equals an instance of the decision tree classifier, and then it's trying to fit these categories, and it's trying to figure out how Y relates to them. So across these variables, how do we figure out Y? How would we predict it? And then here it's saying, oh, we want to visualize this tree, because you'll remember that on this last one, this tree was created. So we want to be able to have that as an output. In order to do that, we need to graph it, and you have to get graph fizz. Remember, if you get this far and you push run and it gives you an error, download the executable and install it, and then restart your computer and then try it again. That's what I had to do. Anyways, I hope you don't have to do that. So here, where were we? Okay, we get the tree, and then, or the data gets ready for the tree, and then we've got the graph, and then we're writing, this is writing the file called mydecisiontree.png. You'll notice I already have a file like that because I've already run this, but this will just overwrite it. And then let's show it. So let's come here. And let's show it. Let's see what happens. Yep, same as, oh, there's our tree. It's a little more complicated than the tree for the comedians, right? We have more, there's more going on in ours. And we've got more rows as well, so there's more that can be differentiated. Okay, so it just kicked it out, and you can, you can enlarge it this way, but we're not going to get very far doing that. So I'm going to bring over that same, oops. I'm going to open this in the main window. Well, it's a little better, right? Can we see it now? Can you see it? And then I'll make it. Okay. So what this is doing is there's a left and a right. Okay. And so anything on this side is going to the left, and anything on that side is going to the right. So win shares, any win shares equal to or less than 7 go to the left, and these go to the right. And in the value, the no's go to the left and the yeses go to the right. So we've got 168 total samples. 401 of them, it's equal to or less than 7 win shares. They're all coming here. Okay. And then this continues until you get a terminal value. The 0 means not an all-star. The 1 means an all-star. And so win shares, we got it. Then we come down here and we've got PER. Okay, so if it's equal to or less than 25.85, go to the left. So there are 424 going to the left. And here we've got one sample, which is an all-star, coming to the right. Okay. I would think you'd have more over here. Anyways, you can see sort of how it goes, right? Let's bring up this chart because they do a nice job, better than I do, of explaining the tree. Where is it? Here it is. So the rank, so this is like we talked about. We'll follow the true. Anything on this side follows the true. Anything on this side follows that this isn't true. And then the Gini represents the quality of the split. So it's between 0 and 0.5, where 0.5 is half the samples go each way, and 0 is they all go one way and none of them go the other way. Samples means that there were 13 comedians, or in our case, what did we have? 400 and some players. And then the next up, the values, 6 and 7 here. It means 6 get a no and 7 get a go. Okay. So when we come back here, we've got 424, which are no's. So if you have fewer than 7 win shares and your PER is below 225.85, your chances of getting in the all-star game are really slim. As opposed to if your win shares are above 7 and your PER is above 20, your chances of getting into the all-star game are extremely high. 22 out of 39 players made the all-star game with that. And so you can follow this tree down, and it follows down all of the examples of not in the all-star game, in the all-star game, that goes all the way around. So here we've got one that clears out 386 players. So fewer than 7 win shares, lower than 25 PER, lower than 21 PER, lower than 17 PER, you are not going to be an all-star. Now, do you see anywhere on here where it lists age? Yeah, we had 1, 2, 3, 3 of them, right? 4. Okay, so we had some that were age. How about, what was that other category that we had? Position. Do you see position anywhere here? POS? I don't. And so what that's telling me is that we could pick a different category and probably get something more useful. That for whatever reason, knowing if they were a center or a forward or a guard, it didn't really help. Okay. So what's left? What's left is to create a prediction. So let's add this code here. And so this is predicting. So we set this. And remember, we've got age, position, PER, win shares. So we set these, and then it checks. If this number becomes a 1, so if it's great, if this is greater than 1, this prediction is greater than 0, then print you're an all-star, get your game on, get paid. And if this is not greater than 0, then enjoy your vacation during All-Star weekend. Okay, so what should we try? What happens if we have a 19-year-old player who is a forward? Again, maybe this column doesn't matter much. Let's say their PER is 10 and their win shares are 6. What's your guess? My guess is they're going to have a vacation. Let's run it. Oops. Yeah, enjoy your vacation during All-Star weekend. Okay, let's keep them 19. They can still be a forward. Let's move their PER up to 20 and give them, let's leave them at 6. Let's try it now. Enjoy your vacation. Now, this can change. You can run the same one multiple times, and you don't always get the same response because it's based on probability. Let's change this. Let's amp this up to 9 win shares. Now let's see what happens. Yes, I probably could have copied the 4 lines into the terminal and just run it there much faster. You're right. Still enjoy your vacation and All-Star weekend. Now, maybe the person is too young. They haven't been in the league very long, so, you know, people don't know about them. What if we change it to 29 instead of 19? And then I'll just copy this and see if we can just run it down here so it'll be faster. Ooh, enjoy your vacation. Let's paste it in again. And let's change the PER up to 23. Still enjoy your vacation. Okay. 26 PER. Enjoy your vacation. 28 PER. That shouldn't matter at all. 10 win shares. Okay, 28 PER. Oops. Let's try 29 PER. Ooh. PER. Well, now I'm just wondering what's going on here. Let's run that same one up here. Maybe I'm doing something wrong. 29, 10 win shares. Enjoy your vacation. Somehow when I change it to 31, okay, apparently no one is going to All-Star Weekend. Nobody. Nobody is an All-Star. Let's try 31 instead of 29. I feel like editing this part out. Let's go back to the decision tree. So win shares greater than 7 should bring us down here. PER of greater than 20 should bring us over here. Age is less or greater than 21 brings us over here. Age of greater than 28. Oh, I see. So we want, if you're younger than 28 and you come here, then that's 17. Oh, wait. Yeah. You're younger than 28 and your PER is greater than 24, then you're in. Okay, so let's try something like that. So a 25-year-old with a 25 PER, 25-year-old with a 25 PER and 8 win shares. $25-year-old, 28 PER. Did we say 8 win shares? Okay, let's try it. And it's going to show up down here. We can't see it. Hey, you're an all-star. Okay, well, sorry for that final 5 minutes of bad television, but trying to figure out the decision tree and how it relates. Now, you should be able to have a higher than 28 PER, and it would be more likely that you get in. But, you know, with more tinkering and more understanding, you know, if you didn't just mimic someone who got in, but you were statistically better than them, you would expect that would increase your chances of getting in as well. Okay, I hope you enjoyed this rather long video, and I hope that it helped you think about machine learning. Find your own data and try this out for your own data. That's the best way to learn.